Okay, so today we're going to talk about waves, some basic information about the types of waves we're going to be discussing, the different parts of the waves, and just a little bit of information about sound. So, first, we're going to start off with just covering some basic vocabulary. There's a few images on this particular slide that I'm just going to use to help guide my conversation. So, looking over on the right hand side, we see a list of some words. So let's first start off by talking about those top two words. An oscillation is basically a vocabulary word for a cycle. Now, when we're talking about a wave, this is something that's going to experience repetitive motion. We're going to be discussing specifically sound waves today, and our sound waves are going to require particles. So let's just go ahead and jump ahead real quick. I think we all understand that we hear sound because there are air molecules that are going to be vibrated, are going to be moving, and those vibrating molecules push against our eardrum, and that pressure is what causes us to be able to hear things. So when we talk about what an oscillation is, or when we say that an oscillation is one cycle, that just means one time through the vibration pattern for those molecules that are carrying the sound waves. Now we're going to talk about different types of waves, because this is just one example that hopefully is very straightforward. So you now understand that an oscillation is one complete cycle or one complete time through the vibration pattern. Equilibrium is a vocabulary word that I'm sure you have heard before in other science classes, and you should have heard it as well in physics prior to now. Equilibrium is a word that means that we're in a balanced state. So as we begin looking at some illustrations today for what a wave looks like, the shape of a wave, the parts of a wave in more detail, we will see that there is a line that kind of splits our wave right through the middle. And so that would be the moment that our oscillating or vibrating particle, or whatever that medium is, would be at its natural, balanced, undisturbed state. So equilibrium will just simply be a reference point for us, and we'll use that for some of our measurements. A restoring force is simply that. It is a force that happens naturally. We have some sort of molecule, or we have some energy that has come and it has disrupted things. And so everything has a normal, natural, balanced state. And so equilibrium would represent that location or that position if things were left alone, where it would be balanced. But since we have this energy that has come and disrupted the balanced state, our object or our molecules are now out of balance. And so naturally there is a force trying to put it back into a balanced state. So if we look down at this illustration here of our person on the swing, right down here, we can see that we all know that if you don't swing, if you just sit, then you would be resting right here at this middle position where you're just simply hanging straight down. But if you have somebody come and pull your swing so that you are now in this position, you are going to experience a force that's going to cause you to return back towards that center or equilibrium position. Now, we all know in the event of a swing, now that we are at some raised position, we have some potential energy, and that potential energy will be transferred into kinetic energy once we are released so that we can begin moving forward. So we won't get into the details too much of what physically happens in a swing, but I think that we can all understand that there is a natural force, and in this case it would be gravity, that causes us to get pulled back towards that center or equilibrium position. And so that's what we refer to as a restoring force. Amplitude is going to be a measurement that basically tells us how far out of position our object or our molecule has moved. So once again, in the example of the swing here, however far we are from that equilibrium position would be our amplitude. And that idea of measuring amplitude from equilibrium is going to be something we will continue to use with our wave discussion today. Mechanical and electromagnetic waves are two categories of waves. Transverse and longitudinal waves are two of the shapes for our waves that we will be discussing today. And then I have some images right down here at the bottom. This specifically is an illustration of a transverse wave, and this is an illustration of a longitudinal wave. And so those are two of the wave shapes we'll be discussing, and we'll get into the details of those parts in just a second. All right, some more basic vocabulary. Actually, this is the same vocabulary that I just went over with you. You can go back and view the PowerPoint that is available on Canvas if you'd like to take some time and read through this a little bit more carefully. So right up here at the top, we have some really important information that I need you to understand. Waves carry energy, okay? So this word energy is super important. When you get asked those conceptual questions, make sure that you always say energy is what is being carried, okay? And it says here that it carries energy through matter and space. And we'll discuss that. The difference between those two situations right now. Mechanical waves and electromagnetic waves are two types of waves. And basically, these are the two forms in which the energy is transferred. So the energy can either be transferred because the waves are being traveled through some sort of what we call a medium. And when we say medium, that is just another word for matter, or maybe it's our type of material. So our medium could be, is the sound or is the whatever wave we're discussing traveling through air? Is it traveling through water? Are these vibrations that are happening through the molecules of some sort of solid metal material? And so those require some sort of physical particles that can then be disrupted. Electromagnetic waves, on the other hand, do not require particles. So you can see our examples here would be things like light and radio waves. And we're going to get into those in more detail in the next chapter. But basically, we all know that light travels through outer space to get from the sun to the earth, and there are no particles in outer space. So in order for the light to travel through space, that means it must be able to travel without the use of those atoms or matter or particles. So we would classify that as an electromagnetic wave. In this chapter, you see I have my little yellow asterisk over here. We are going to be discussing mechanical waves in detail for this particular chapter. So now that we know that we're going to be classifying, or we're going to be discussing the classification of mechanical waves in more detail, let's talk real quickly about two shapes that our waves are going to appear. So we have transverse waves, and it says waves oscillate perpendicular to the direction of the energy. And then we have longitudinal waves, where the waves oscillate parallel to the direction of the energy. So we have a couple of illustrations here. A transverse wave is a wave where we have our matter, our particles are going to oscillate and they're going to vibrate. They're going to move back and forth in a direction that is perpendicular 90 degrees at a right angle to the direction that the energy itself is traveling. So this illustration is actually an animation that I apologize is not working at the moment. But what we would see if we were looking at this animation is that we would have this wave, and it's going to follow this path, and our wave typically would appear as though it is moving right to left across the screen. These colored blocks represent our molecules, our particles that are going to be vibrated or oscillated. And so even though the wave travels to the right across the screen, this one molecule right here actually would just end up bouncing up and down, never actually moving across the page just vibrating or oscillating in this space right here. And that's what all of these molecules would do. The red molecules don't represent anything different. It's just a way of showing us our highs and lows on our illustration, and we'll understand why those highs and lows matter here in just a moment. But all of these molecules would just be vibrating or oscillating up and down, whereas the energy itself would be traveling in this particular animation or example horizontally or to the right. And so you can see that those indeed are perpendicular directions to each other. This right here is an animation that will work for us. So again, the molecules themselves are bouncing or vibrating up and down. Pick a dot and follow it, and you'll see that it's not traveling across the page. It's just bouncing up and down while the wave itself appears to be traveling to the right. Okay, so let's now talk about our transverse wave and all of its specific parts. So our transverse wave has a crest, which is simply a fancy word for the highest point, the trough, which is a word for the lowest point, and then we have our amplitude, which is a displacement that is being measured from equilibrium. So when we talk about that equilibrium line, remember we talked about it is a location on our wave that basically cuts our wave in half. So this line right here would be our equilibrium. If we say that our molecules are going to be oscillating or vibrating so that they go up and down like this, then if we were to measure how far does this molecule move from its equilibrium point, then our amplitude would not be measured all the way from the top to the very bottom, but it would simply be measured from that midline to the highest point or the crest, or we could measure it from that midline to the lowest point or to the trough. So please make sure if you're being asked to interpret any questions that you understand that it is only from the equilibrium point. If you get an illustration that tries to tell you that the amplitude is this length, that would be incorrect. So please make sure you know not to mark that. Okay? All right. Notice that it says over here that you need to know and be able to label the parts because you will be asked to do that in the future. All right? Okay. The wavelength is basically a way for us to measure the length horizontally in meters of one complete wave cycle or one complete oscillation. So this particular illustration you can see has the wavelength measured in multiple locations. It's very common for us to define the wavelength as how far apart it is from crest to crest or trough to trough, and honestly that's really because those are the easiest points to have a definitive location to measure from, but it really doesn't matter at what point on the wave you begin measuring, but you must allow it to complete one full cycle. So it must have both the up and the down, the high and the low, the crest and the trough in that complete wave. You can see down here that this is a measure in meters, so that means that it is going to be a variable for us and it will show up on illustrations sometimes. So if we are illustrating or representing mathematically our wavelength, it's going to be illustrated with this symbol right here, and that is pronounced lambda. That is pronounced lambda, and it is a Greek letter, and you will see that on some illustrations here in the future. All right, our second wave shape has two names. It's called a compression or a longitudinal wave. I more often use the word longitudinal, but they are representing the same wave. It doesn't really matter which word you use. So longitudinal waves, the matter is going to now oscillate in the same direction that the energy is traveling. And so here you can see that it says it's parallel to the energy. So if we were to look at an animation, we would see that our waves our energy is going to be moving horizontally, and then these little rings here represent our molecules. So if we were talking about a sound wave, sound is a longitudinal wave. And so what happens is that the air molecules are actually just going to vibrate back and forth, just like the other animation that we saw. So what we have is an area where our air molecules are really tightly packed in together here. And so we naturally call it the compression area because the air molecules have physically been squished together or compressed. And so that leaves an area where the molecules are extra spread out because there is a relaxation point or some extra space as a result of us squishing these molecules together. So the area where they are spread out is referred to as the rarefaction. And I do want to point out that yes, we can still identify a wavelength here. You simply need to allow one complete time through the pattern. So if we started a compression, then our wavelength would end when we get to the next compression. So this would be our wavelength. And really, just like I said before, you can measure your wavelength at any point on your wave. You just need to make sure that you allow it to complete one full pattern or one full oscillation or cycle. Okay? All right, moving on. Oops. There's an animation for you, and you can see that here the molecules are being squished together, and so they're leaving in these patterns of condensed molecules. Here's just a side-by-side. You have some examples with the slinky. You guys are actually going to do a lab later this week where you will either be using a slinky if you have access to one at home or watching a video of a slinky going through some of the motions. But you can see here that we can represent both the longitudinal wave and a transverse wave. Our longitudinal wave, we would simply squish some of these slinkies together, and that would cause the energy to be passed through the other coils of the slinky. Here, in order to create a transverse wave, you would need to move your hand up and down. Or I guess if you're doing this horizontally, it could be right to left if it's laying along the floor. And that is going to create your transverse wave where the molecules, or in this case, the slinky, is moving vertically while the energy is moving horizontally. All right, just a couple more vocabulary words about our waves. We are going to be asking you to interpret the period of a wave. So let's define that word. Period is going to be represented with a capital letter T. And a lot of times students have a little bit of an issue. Why a T for period? Shouldn't it be a P? But if we look at our definition, period is actually a measurement of time, okay? It's not a lowercase t for time. It's a capital T for time because it is specifically the amount of time for only one oscillation. So I want you to remember, make a mental note, period is measuring the time, but it's the amount of time for one oscillation. Here I have a graph that is showing us the highs and lows, the crests and troughs, the compression and rarefaction phases of our wave. And so if we were looking at this particular graph to figure out the period of our wave, you can see that we have our time measured here in seconds along the x-axis. So one complete wave or one complete oscillation would end at 10 seconds. So the period of the wave in this graph is 10 seconds. The next vocabulary word is frequency, and frequency is going to be a measure of how often a wave occurs for each second of time. Be very careful. There's a lot of similar words being used in these two definitions, so it's really easy to get them confused. You can see in red, I have kind of simplified or highlighted the definition. Frequency of the number of times a wave oscillates each second, but you can see in parentheses, I've used some other words to maybe help you have a better understanding, but be prepared for your quiz for the questions to be using the word time, oscillation, seconds very often. So make sure you know these definitions really well, okay? Frequency is going to be indicated with a lowercase f. Capital F will still be for force. So frequency is a lowercase f, and we're counting. See our little guy here? He's counting on his fingers. How many times did that wave pass by before the 1 second timer goes off? Okay, and then I have some graphs here just showing you some examples, and you can practice on your own looking back at those illustrations later and counting how many waves in the 1 second of time on each of these graphs to see how I came up with those frequency values. All right, now I just have one quick slide about sound specifically. So sound is a longitudinal wave. You must know the shape of a sound wave is longitudinal. It's very important information. All waves are going to have the properties we just discussed. So if we're talking specifically of a sound wave, then it is going to have a frequency, and that frequency is going to correspond with the pitch that we hear. So in other words, a high-pitched sound or a low-pitched sound will correspond to a high frequency, meaning we have several waves that occur within the 1 second of time. A low-pitched sound would have a low frequency, meaning we have very few waves that occur in that 1 second timer. Our amplitude is going to represent the intensity. Now remember, amplitude was that displacement from equilibrium. So when we talk about sound, how intense a sound is really how loud that sound is. So I put over here in parentheses volume, but I want you to correspond the word amplitude with the intensity. And because we're talking with sound, it is common for us to use the word volume in that question. Notice once again, I've commented for you that you need to know these facts. There's some additional information down here about the speed of a wave, and I just want to take a moment. We're going to talk about some math with our waves on another session, but for right now I just want to briefly discuss with you. We should be able to use the frequency and the wavelength to determine the speed of a wave. And that's true for all waves. But when we're talking about sound waves in particular, we'll often talk about sound traveling through a material. So how fast a sound wave travels through a material is going to depend on the material itself. So the molecules in that material, how close together are they, how far apart they are, is going to affect how quickly that energy is passed from molecule to molecule. And so that's what these bottom three little bullet points are about. So once again, you can read over those by looking at the PowerPoint. Take a little bit more time to read through that, but we'll address these as needed as we come to our math session at a later time. Okay? All right. Well, those were the things that I wanted to discuss with you for today. Just talking about some basic information about waves. So make sure that you go through those PowerPoints and read through those slides in more detail, and then practice that assignment that corresponds with today's notes. I hope you guys are having a great day. Bye.